State-of-the-art video stabilization tools such as YouTube, Adobe's Warp Stabilizer, and bundled paths might not give satisfactory results if the input video is too challenging, such as the one on the left. We present a user-assisted video stabilization algorithm that takes the baseline bundled paths output as input, as well as user input to produce an improved video stabilization. Notice that in our result, the background does not wander around as much as the baseline. Also, notice that the walls on the right does not sway as much. Here is how our system works. We start with our implementation of bundled paths. One reason why the stabilized video is not satisfactory is because tracks used to guide the warp do not belong to the background. In our work, we cluster tracks based on their trajectories and allow users to modify track selection by toggling the track clusters using the mouse. Brightly colored tracks are selected and gray tracks are pruned. Notice how the user removes tracks on the dynamic objects in the video. Here, we show the input video stabilized with only background tracks. Notice while the output is improved over the initial result, the background and the walls still move and sway. This is because the algorithm does not have any semantic information about the video. To remedy this, we allow the user to specify how regions in the output video should look. The user draw quadrilaterals and deform the region by dragging the corners of the quad. The region is remapped in real time to provide user feedback. We then solve for a stabilized output where the user-provided region constraints are met. This is our final result. Notice that the background and walls do not sway as much. The vertical structures on the right remains vertical as well. Let us take a closer look at another example. In this input video, we have erratic camera motion and dynamic objects moving in the scene. The baseline stabilization is not satisfactory as there's a large sudden jerk on the left wall. Let's look at the tracks used to guide this warp. At the time frame where there is a large jerk, many tracks with different motions are selected. This conflict causes the warp frame to deform drastically. To resolve this, we have the user click on clusters of tracks that are on dynamic objects that are causing the deformation. Tracks at the extreme of the frame are partly responsible for the deformation because the wide field of view and large depth introduces tracks with large movements there. Therefore, we remove tracks around the extremes for this time period. We use the user-selected tracks to stabilize the video again. Notice how the sudden jerk is reduced with a better track selection. While the video is better, there is still room for improvement. The user then adds region constraints by drawing quads on frames and specifying where she would like them to be. The faded frames show the original position before the user edits. In this example, the quads encompasses the entire frame, but it could be only for a small region as well. We then use the user-provided region constraints to guide the stabilization, such that the output video should be smooth and have the appearance of these user-specified regions. Notice that the jerk is reduced, and the camera path is smoother now. We also compare our result with Adobe's Warp Stabilizer. The buildings in our result does not sway as much as Warp Stabilizer's result. Similarly, our result when compared to YouTube's video stabilization tool performs better with less unwanted camera motion and wobble. In this input video, the baseline result still has residue camera motion and the background sways a bit. The user corrects track selection by removing tracks on dynamic objects. Here, we show the user-drawn region constraints. The video on the right is our result. Notice that the video is much smoother and the structures stay upright. Here is our result again. In this input video, the baseline result is skewed. The user removed tracks on objects that are very close to the camera, as tracks on nearer objects have larger displacements compared to the background. Here we show the user-drawn constraints to rectify the video. Our result is on the right. Notice that the sandcastle is upright. The large camera motions result in a stabilized video swaying. The user removes tracks on dynamic objects as well as providing region constraints for the video. Notice how our result is smoother and the structures are vertical. We show our result again. Structures in the baseline result is skewed due to the large range of depth in the input video. The user does not make any modifications to the track selection, but instead provides region constraints. The output video is improved as the content of the videos are not distorted. For more results and detailed comparisons with other stabilization algorithms, please take a look at our supplementary material. Thank you.